Um, hi. Just a comment before we start. I added in the deliverables section two links to one of the of two on two videos. One I'm going to share it with you during this session, and the other I'm asking you to have a look on your own. The one that you have a look on your own is a virtual visit to the Barcelona Supercomputing Center. And so, well, that you can visit, and it's very interactive, and so in that way you can get acquainted with it. And the second one is something that we are going to see together at some point in this session, because it's about why do we need high performance computing? Okay, so it's important. Out of the some of the questions that came up in the not yesterday but the last week, I think that it is important that we are all on the same page on why are we learning and why are we struggling with these MapReduce stories, and why it is important and how it is related to both the course, but particularly to your professional career. That's the most important thing ever in life now. But before that, we are going to have a little bit of tequila, because we are. I'm going to introduce a little bit technical aspects in part of the session. Then we will have a break with the video, and then with a discussion, and then so that you can breathe um, out of the technical uh, presentation. So, right. So as I said, March is devoted to women, and I will continue sharing some information, valuable information, particularly to our female colleagues. But then I promise that since I have stated that here we promote diversity and inclusion, next month we will include men in the story, and I will start sharing opportunities that you can consider in your professional career. But anyway, we are still in March, and an important thing that is emerging in many contexts is projects that people can develop, and that come to complement the skills that you have and you develop as you study, and then as you develop your professional career. And an important one is the README project provided by GitHub. And if you Google it and see what is going on there, you will see that there are many sub projects that that you can be included, and you can promote, etc., and participate. And then there are descriptions of possible career destinations that you can consider. So regarding, for example, on the top of the screen, you have learning to decentralize, bringing hardware hacking to the masses, then other more social projects that can be devoted. I mean, that can be addressed using computing. And then there is a very nice one, which is PyLadies, creating a welcome world for women in open source. So that is, as you have seen probably during your education, a huge movement on open source, and GitHub is a nice platform in order to develop and join to open source projects. So even if I mean, being a woman or a man, if you are interested in joining, interesting projects, development projects, have a look at them, because it's a very good experience for you in order to address collectively the construction of solutions, and particularly in a high-scale manner. Okay, so well, that's the publicity. And then now going to our matters. We have been having a look on design strategies in order to produce MapReduce algorithms. And we have concentrated for the time being a lot on the data structures. I know that I have insisted a lot on data structures, and this challenge, which can be stated as given any data collection in any format, how do I represent it under a key value data structure, where the key and the value can themselves be of atomic types or of complex data types. Okay, so that's huge challenge, a design challenge. And then the other aspect is that we have been concentrating a lot on this map and these reduce functions. And we haven't had a look a lot on these intermediate shuffle and sort aspects that in fact we have to design too. I have insisted that these aspects are delegated to the infrastructure, but because of performance reasons, it is better that we delegate the less possible to the infrastructure, because the infrastructure is something that we do not control totally. And that has to do also with the configuration, the tuning that someone else can do for us. Okay, so the person that manages the clusters, so it's not us that will manage the cluster, this manager will configure the type of resources and the number of resources that will be allocated in order for us to run our programs. And so since we do not control this, we would rather have a very nice design, very optimized design, controlled by us, and then use the infrastructure. And so in these terms, we have seen that, in fact, the map function is associated with three processes. Okay, so if we think about, in terms of process, about the map function, in fact, it is implemented by three processes. The mapper, which is the one that executes the algorithm, I mean the function that we write for associated to map, and then two additional ones. One that is the combiner that will reorganize in some way the results, and then the partitioner, which is the one that will reorganize the data across the cluster so that the reduced processes can start. Okay. And the question here is, what do I program within the map, within the combiner and the partitioner? Okay. So because me programmer have to do that job. And then in the reduced part, again, we have these famous two processes that shuffle and sort to deal with, and of course the reducer that will perform the aggregative aspect of the process. And well, the design question here is whether we really need combiners and partitioners in order to implement our map process. and whether we need complex shuffle and sort processes in order to prepare the data to be aggregated in the reduce function. Okay, so that's the objective of the game that we have to answer. And well, people have already thought a lot about this. We are almost like 10 or something years after the first time that MapReduce was first proposed. So there have been people addressing the problems. And today, it's been also like a long time, that there exist map-reduce design patterns that we can use and that can help us do this design that I have introduced before. So, well, there you have the book. It's an overview book, and it addresses, I mean, the book is divided into groups of design patterns. It's like when, you know, professional skaters in the Olympic Games, you have to be able to perform the fundamental forms that can ensure that you have the required official level, fundamental level of knowledge of MapReduce. And then there is a second aspect, which is the advanced, there when you have to be creative, and the book addresses these two design patterns, families. So, but here we are going to have a look at the first part, because ideally, what you would expect as learning outcome out of this part is that you feel as comfortable as possible on the implementation of algorithms of the different families of the fundamental MapReduce algorithm. Okay, so that's ideally what we're seeking for. I hope that we will achieve this objective. Now we have a heart attack because we have to learn all this. So the MapReduce patterns are basic forms are organized into 4 families. And then what it's nice of it's design patterns. So it's that you have the 4 families, sorry. You have the subfamilies with the enumeration of the type of operations that refer to which these subfamilies refer to. And then, as we will see later on, for all of them, you have a generic setting of problem, design of your data structure, and then implementation on these map combiner, partitioner, and reducer. Okay, so that's the generic. So the 4 families are families that we all know, particularly you that are in the last part of your education, undergraduate education. So you have addressed these algorithms. Okay, so summarization is the very basic one. So this one, at the end of this part of the course, you have to make sure that you have full control on this. So for numerization, we have 3 subfamilies. The so-called numerical family, which includes being able to compute the minimum, the maximum, count, average, median, and standard deviation. Okay, so for the time being, what we have worked together is count, the counting words. It's an example of count. And with the second example, we addressed minimum, maximum, and count. Right? Do you remember the one where we have to count the posts of a set of users and say the first time within an interval of time that the person posted something and the last time. So that's combining minimum, maximum, and count. Okay, so in other exercise that I will ask you to do, sorry, I have something here. Okay, sorry. I will ask you to address average, median, and standard deviation, which are more or less the same principle. Okay, so it might change a little bit depending on the input, but you will see that it's more or less the same pattern. Okay, so that's first of family. For the time being, we have addressed the key operations of this. So first question that you on your own have to think about is, am I able to design a map-reduced solution for computing the minimum of some set of items, the maximum, count elements, and that's it, okay, for the time being. And then later on, average, median, and standard deviation. Okay. The second family is a very important family because it's related to a key solution used for web information retrieval. Okay, so and this data structure is called inverted index, and the idea is how to build inverted indexes on top of the collections of documents, understood HTML or textual documents, okay, in order to represent their content under an inverted index. I remind you that an inverted index says for a given term, which are the documents in which this term appears and in which position. So that if I'm looking for map within a collection of terms, it will tell me map appears in document 3, 5, and 7 at position something. Okay, and the position is the number of items in the document. Okay, and so this is fancy because with this index, the index will prevent the information retrieval algorithm to go and explore all the documents of a data collection given a keyword query. And well, of course, here I'm occupying your brains on map-reduced designs, but you have to make sure that you know the principle in centralized, okay, in classic programming, and that then you transform it into the map-reduced setting. Okay, this is very important that you master because this is a glass door question. So anyone with basic knowledge in computing systems engineering must know this. Okay? Quite important. And then the third subfamily is counter with counters, which is in fact an optimization of the techniques that we apply here. Okay, so for example, count number of records, a small number of unique instances, summations. Okay, summations are examples of counting counters. Okay, number of users per state. So these kind of examples are solved in using this technique, counting with counters. Okay, so this is the very first family. I would say that this is more than fundamental, so numerical and inverted index solutions. And then counting with counters, I would say that you can stay with the principle of the solution and making sure that you can identify, given a problem, that this problem is referred to counter and counters and that you can apply the pattern, okay? Even if you do not master the counter of counters. Okay, so that's the target for this part of the course. Second family. Second family is all about filtering. Okay, so as you have seen in your, I don't know, how long have you been studying? 4 years, I suppose. So during these 3-4 years that you have studied, filtering is a very important operation. And in fact, there are 4 types of filters, that 4 families of filters that should be known by a computing engineer. First of all is classical filtering, which is, for example, having a closer view of data, tracking events within threads, do a distributed grep. For example, the first example that we performed in order to test that Hadoop was doing fine was a grep. Okay, so in fact, any lookup function that is implemented, for example, in Unix for exploring the files manually on terminal are filters. Okay, so this is important. Then there is a lot of filtering used for data cleaning. That we have seen in the part where we saw these data science experiments. There is a lot of, for example, searching for null values and substituting them with some specific value. And so this kind of exercises are filtering. Then random sampling, removing low scoring data, as I have said. So all these examples of operations are solved by filters. Okay, that is something that you perfectly know because of 2 reasons: because you know SQL, because now you know how to query graphs and documents, and you have, I think that you have studied flowers, no, for searching on within JSONs. No, I think that you have done this, and in another course, and then and you know now pandas. And in pandas, the library provides a lot of filters. Okay, and so those filters are officially implemented in an imperative manner, centralized manner. The idea is that you know how to transform this operation into a MapReduce solution. Then there is a very, again, important family. It's in fact a type of filter, which is called Bloom. The Bloom filter, again, this is a Glassdoor question. Okay, Bloom filters at the beginning of the history of computing were intended to identify operations that have to be done on top of a limited architecture in terms of CPU. Okay? So instead of sending requests and requests and requests and exhausting the CPU, the idea was to identify and group together similar functions and then send them according to the occupation of the CPU. And today, Bloom filter is quite used in big data processing. Okay, so, and also to control that, we will see by the end of this course, but I'm going to give you the hint now. When you use the cloud, every request that you send, being a request that doesn't imply data or that puts data into the cycle, it has a cost. And so people have come up with ideas of having something that is called function as a service, and aggregate many functions, as much as functions as possible, out of the cloud, and decide whether these functions can be executed either, in the external arena of the cloud, either on the fog or on the edge, and then only send the absolutely necessary operations to the cloud. Okay, and this filtering, deciding which are those operations that are really delegated to the cloud and those that are executed on the fog and on the edge, that is done using Bloom filters. And so this is why Bloom filter is a very important type of filter. And then there are two other classic ones, which is the top 10, top something, no? The top 10 algorithms implemented in MapReduce, the top 10 users implementing, having obtained prices on Kaggle, etc. Okay, so this top something operation is an important filter, and then avoiding distinct, okay, distinct, which we know from SQL, is a major filtering type and can be also implemented under the MapReduce setting. Do you have questions until here? Please.
Hello, teacher. Yes, I have a question regarding Bloom. It's just that I didn't understand it.
You did well. We will go through Bloom in a deep manner. Here I'm just giving the picture, but the idea is that instead of sending every operator, you're a processor, okay? So if you're a processor, instead of systematically processing everything that you receive as task, the other process that is sending you these requests will keep the request like on batch and filter those that really need to be executed at some point in time. Okay, and in order to form these families of functions that are grouped together in order to better exploit the CPU, is done via Bloom filter. This is a general principle. As I said, we will go through Bloom filtering concretely, but this is the principle of them. Okay, so filtering operations that look more or less the same, and then preventing sending them to be executed to some CPU or whatever until it's necessary or it's pertinent to do.
Oh, okay.
And then,
Thank you.
right, and then you can reason, of course, about functions and also about data. If you are, for example, if you are main memory, now you are main memory, and so you have a lot of data within your space. You have data. And then at what point are you going to send the data back to the disk because you are exhausted and you cannot deal with more data anymore? Or at what time are you going to keep them in cache? You have to decide who goes to cache and who goes back to disk. And in order to do that, you can use a Bloom filter to filter your data and do this kind of decisions, make this kind of decisions. Okay, so these are for example, well, here it's H-based queries are done with this. Many NoSQL systems internally work like that in order to resist charge. No. Okay, so that's so again, what do you need to make sure that you know? Well, classic filtering you already know. The only thing is that you have to make sure that you can design solutions under the MapReduce setting. So that's more or less simple. Then top 10, you will see that it's very simple to do, but you have to bear in mind which are the possible ways of implementing top 10, including with the MapReduce setting, okay? distinct too, but you are already acquainted with distinct. It's eliminating duplicates, and so you have to make sure again that you are acquainted with the different strategies on how to implement distinct, including the MapReduce setting. Okay. Of course, here in my course, I will assume that you know the other strategies to implement distinct, and I'm only going to introduce the MapReduce setting. But you, as we have been insisting, under control of your knowledge, you have to make sure that you know all this. Okay? This is very important. And then Bloom, I believe that Bloom is kind of new, and so that one will be the fancy part of this part of the course, and we will go through Bloom in a deeper manner, right? It's very cool, Bloom. I like it very much. You'll see. These are the two, well, we can say basic ones. Let's say basic ones. And then there are two supplementary ones that are more associated to big data processing knowledge. Okay, people that are officially promote themselves as people able of processing big data have to make sure that these two families are controlled in his or her knowledge. First of all, of course, data organization. And that, I mean, you can guess if we are dealing with data and we are dealing with volume or with velocity, of course, that at some point, in order to resist volume or velocity, we need to organize the data. And organize it where? Well, in the clusters, because we stopped working in centralized computers. Now we work on clusters, and now we work on the cloud. Okay, so we have taken off from classic architectures. And so regarding data organization, well, we have to structure the data in some manners. One of the manners is organizing it hierarchically. This hierarchical organization of the data is used within the engine of any database management system, being relational or NoSQL. And this is in order to prepare the data such that the operations can be executed faster and with less overhead possible. Remember that we as computing engineers, when we develop algorithmic solutions, what we are seeking for, there are two basic measures, and then with the cloud there is a third one. We are seeking for performance in terms of time. We want to be as fast as possible, okay, in the execution of our algorithms. We are seeking for reducing memory. And these two, we have, I mean, I do not remember if there is still this ACM contest, but if there is, you will see that normally all the problems that are provided, you have to optimize them, manage your solutions in terms of time and in terms of memory consumption. So that's two aspects. And when we introduce the cloud, we are also thinking about reducing as much as possible the economic costs. Okay? So that's the problems that we keep in many contexts solving. Okay, that's our solutions are guided with respect to these three constraints, and this is all the game about building solutions. So structuring data is a way of making sure that operations on top of this data will create less overhead and therefore not penalize execution time. That's one thing. And then For example, well, that's for DBMS, but then if you want to organize, let's say, Stack Overflow posts out of the past and a long time, okay, you are going to need to implement structured organization of your data, building question and answer solutions. That's another example of client of this hierarchical organization of data. And so we are looking for algorithms that let us, out of a given data collection, to provide a hierarchical organization of this data collection. Then partitioning, that's cool because partitioning is a famous problem that can be implemented under MapReduce in order to reduce time. Okay, there is binning that is also a way of organizing the data. Then all sorts that we know because we spent many hours, programming hours in our first courses doing sorts. Okay, so sorts are back here, but now we have to implement them under MapReduce settings. And then shuffling also is a way of organizing the data, and this is also an important thing to know. So again, I would say that for this course, well, structured hierarchically, you will see that it's almost gratis because you already know this, but then total order and shuffling would be those that will be fancy new and that you have to pay attention on them. And then a wonderful function, one that is recurrent, that is used to answer many, many questions, is in fact correlation. Very often we need to correlate data in order to have an understanding of what it represents, of a specific behavior, etc. So correlation is a key operation. And when we talk about data, correlation is specialized into the notion of join. And join, from the relational model, but join can be generalized out of the relational model. You have seen in the course, in the exercises that we have addressed, there were examples in MongoDB showing how to do joins, which is correlating documents, and it is possible, much more costly, but it is possible to perform joins on graphs. Okay. In fact, there are many implementations of joins, and all these implementations are implemented in any relational database system. Okay, so when we write in SQL a join expression, in fact, the internally the system, according to the previous statistics that it has and according to the schema, will decide which is the best implementation of join to use in order that the query is executed fast. Okay, and also depending on the indexes it has. Okay, so given a query, the execution plan and the knowledge of indexes that have been designed internally within the system, it will decide which is the best join that can be used in order to answer your query. Okay, and so this one, well, if you have to master some of the previous one, the joins, there you pay attention. Okay, so there are at least 5 important operations that can be used in order to implement some version of join. There is the reduce site join with Bloom filter, the replicated join, composite joins, and then a a flexible initial version of join, which is a Cartesian product. Okay, so Cartesian product in MapReduce, of course, you must. Okay, after the course, you know how to do it. And then the others, you have to know the principle. And we will see that when we start touching joins, we are also starting to touch the limitations of the MapReduce programming model. Okay, and we have to have a more intelligent, tricky way of understanding MapReduce in order to implement joins, because all the operations that are represented in the previous three families are unary operations. Okay. Whereas join is a binary operations, and there you have to see, but what about a binary operation if you have taught us that map only receives one input? How are we going to do with respect to the fact that join needs to operate operands? You know? Well, we have touched the limit of MapReduce, and we will see that people have worked a lot in providing solutions, and this obliged people to sit down and think about alternatives on how to parallelize easily data processing without having to do tricky things in a more natural manner, and this will lead us later on to data oriented solutions with MapReduce. Okay, so this is the overview. Okay, so and it is your checklist, right? So remember, at the end, at some point, I will tell you and I will say we are going to do a challenge with this, and you will tick this checklist and you make sure that you know how to you know what it is about and how to implement this. Okay. Questions before we continue, please.
I have a question regarding uh, the limit of MapReduce. So I know that join needs two operands, but so does MapReduce still use join, or I didn't
Yes,
understand well the
there are
context.
yes, if you remember here we only have one input, which
Oh,
is the key value. But for implementing a join, we have to have the left side and the right side of the join. So we have to figure out how to, even if we receive one collection here, how to partition it such that one of the piece of the elements is associated to the operand to the left, and which subset is associated to the right operand. Because at the beginning we're going to have a bunch of left and right all put together. And now the first thing that our solution has to do is divide them into two, identifying which is the left and the right side, and then operate on join. You see the challenge?
okay, so we have to do like extra steps, right?
Yes, extra steps. And how are we going to identify which is the real right and the real left?
Okay.
You see, that's okay. We can partition in any way, but this is not the idea. No? We will have to figure out who is who, and this is the design challenge of the joints in this MapReduce version that we are studying, more or less.
Yes, yes, yes. I understand it.
Okay.
Thank you.
Mm. In fact, just for the little story, you know who is Jeffrey Ullman, right?
It sounds
No, sir.
familiar, but I don't know.
Did you study algorithms, compilers? There is a famous book, and there is a knight in the cover of the book, a dragon with a dragon.
Principles of
Yes, with a
computer.
dragon. Yes, yes, yes. That one is by Ullman and Aho, I think. Um, so they wrote this famous book. I think that all of us before my mother is computer scientist, and well, my mother is now 75 years old, and she studied uh, compilers with that book. Okay, and in her master now. And then I studied in my undergraduate studies with that book, and I believe that you studied with that book. Okay, so this is the book. Okay, so but Ullman has not only done this job, and there is a very nice book that we are going to use when we will address joints, and it is by Ullman and his team. And because of compilers and because of this fundamental study of MapReduce with his team, he obtained last year the Turing Award. Okay, together with us. So you see, there we are really on the limits of current technology, understanding them, and then having a look on trendy solutions that are around now, and then how do we come up with these solutions, and how do we move forward out of the limits of MapReduce. So that's what we are doing in this joint part. That was for the little story. As little story, it's not English. It's um, a comment in a way of speaking in French, which means they are chatty, just for chatting, just for gossiping. Okay, so we are gossiping about computing systems history. Okay, so let's move on. Now what I'm going to do, again, I apologize for this blah blah in this session. Afterwards, I will leave some homework with algorithms, and we will have a more interactive session. But, well, now I'm obliged to do blah blah. So let's have a look on how do patterns look like. Okay. So here we have summarization, and then we have the three subfamilies representing summarization. And so the book is online. Okay, so if you have a look at the book, what you have is the numerical summarization pattern, and the patterns are described into three elements. The first element is, of course, a general description of the pattern, and then the pattern provides an intent and a motivation and applicability. So this is for the generic family. Okay, so the intent for numerical summarization is group records together. So that the intent is the principle, okay? The general idea on how you do things to any problem that is associated to summarization is you group records together by key and calculate a numerical aggregate per group to get a top-level view of the larger data set. Okay, so you are going to count words, you organize your data into term and something and value, and then what you do is you are going to make this organization, and then you operate on the value, okay, and you do summation. So, or you can do maximum, or you can do count, or you can do whatever you need, okay? Any aggregate that you operate on the value. And such that you end up with groups of results out of applying this aggregate function. If theta is a generical summarization function, the idea is that we wish to execute over a list of values, which you have here. So these are the flat values. You are going to try to find the value lambda such that lambda is the result of applying theta, the function, on top of this set of values. And theta can be minimum, maximum, average, median, and standard deviation. Okay, so which are the examples of operations that are related to this numerical aspect. And then why do we need that? Well, because sometimes we want to group logins by the hour and the day and perform a count on the number of records of each group. We would like to group advertisements by types to determine how effective our ads are for better targeting. So now we are Amazon Mix, and now we provide advertisements to our users, and we would like to determine whether we are really targeting the intended market with our ads. So this is a classic use of this kind of generic pattern. We want to deal with numerical data or with counting, and the data can be grouped by specific fields. Okay, so the principle, that's something that some of you came up with when I introduced the count. Some of you were saying, okay, why don't we do a hash solution? Well, what the reflex is right, okay? The reflex is let's group data together, and then let's apply the function, the aggregation function on top of the groups, and then we integrate, and that's it. So that's the right reflection. So the exception is that here, since we have this key value restriction, we cannot directly hash anything, and so our map function will create the groups, and then such that then we can apply the function. Okay, so that's the generic principle of the implementation of this summarization that I think that now you master, because we have been around the counting words for some days. And then out of this generic pattern, we can think about how are we going to implement this, to deploy this in an architecture, okay? So here, the question is, the mappers that I need, whether I need these intermediate operations to prepare the results of the map, such that the reducer, the tasks that have to be done by the reducer are reduced, are minimized. So again, the mapper outputs the key that in fact represent the group by. In fact, what we do when we address this pattern, in all cases, what we are implementing in the map function is a group by. Okay. So, and then it depends on what we have in the value and the key. The group by will be harder or less hard, but it's a group by. Okay, and we have explicitly to implement it. Okay, there is no library group by. Okay, it's up to us to implement. And then now the combiner can do many things. Remember that in the first setting of count, what we produce is term and one, term and one, term and one. But this creates overhead, because who is going to create the other aggregation where we eliminated duplicates and we aggregated into a data structure the ones? Well, this can be delegated to processes called partitioners that are going to do the job. And then, well, the reducers, well, these guys do that job, and then the reducers, well, here they are even ordered, and then when the reducer receives the input, it's ordered and it has been prepared such that the reduced functions, which is summation, will go very fast. And of course, here, what I'm not saying, and that you might be thinking about, is how many mappers, how many partitioners, and how many reducers, okay? So first, before that, well, the number is tuned by the configuration of the infrastructure. Okay? So that's not our problem. However, our problem is, as I said, whether these partitioners will exist or not. In the case of this family, the pattern says that we can have simple mappers and that every mapper can have an associated partition. Okay, and then partitioners will be the ones that will communicate with the reducers. Okay, so that's the pattern who says that. And how did we come up with this? By making many tests. So people started using MapReduce and testing and testing and testing, and they came up with this result. And this is why this became a pattern. Okay, so that's the way we know it, by experimentation, but not by us, by others that came before us. Now, the other interesting thing about these MapReduce patterns is that they make the book makes connection with other strategies that are used in order to process data. And these are two important languages that are used in order to process data. The first one is SQL. So what the book says is, in MapReduce, the pattern, implementation pattern is like that, and you should consider partitioners associated to each mapper. No? And then if you are looking for equivalent implementations of this imperative implementation, you can have a look at expressions of SQL that use group by. And then there is another language that we won't study here, but that it's a declarative version of data processing when there is no relational behind, and when we are using MapReduce, the language is called PIG. It was proposed by Yahoo a long time ago, and so they came up with a kind of semi-declarative language that could be used in order to do the same operations as with MapReduce, but in a declarative manner. So that's big. In fact, there are two main languages that were proposed in this setting. One is Pig from Yahoo, but Yahoo stopped existing in research and development. And then Dryad from Microsoft. So that's the way these patterns are represented. So what is important to bear in mind until here is that the pattern will tell you which is the operation that you have to implement in the map, which is the operation that you are going to implement in the reduce, and which are the operations, if necessary, that you have to implement, that have to be implemented by a partition. Okay, and if you decide to use partitioners given the pattern, then you will ask the person that tunes your Hadoop environment to configure it such that it knows that you are going to use mapper partitioners and how much resources will be allocated to all these processes. Now, what is, in your opinion, the disadvantage of having these partitioners between these two mappers and reducers groups of processes? Can there be some disadvantages? No ideas? What happens if we, let's think about object-oriented programming. What happens if suddenly your programs, you create a lot of object instances that are running in, your machine?
Does the stack get full?
Yes, I mean, we are using a lot of resources. At some point, the stack will overflow, and we will have problems. And if we are reaching that, at some point, these processes will create overhead. The operating system has to take care about all these objects that are there, consuming time and resources, and that might not be doing anything. And this is why the garbage collector exists, okay? Because it gets rid of objects that are there but are useless, such that they do not create overhead on the execution of your programs. And the other thing is that if you, in a distributed setting, for example, when you use RMI, if you have many objects, distributed objects that have to interact, you create overhead on message passing. All these processes need to communicate, for example, between the mappers. Well, here we have 3, there is no huge problem, but now imagine that here we have 10K mappers, and that have to communicate to 10K partitioners. And all these has a cost, because it's not only communicating the mapper with the partitioner, but it's also that they are going to exchange data. So you need all the HDFS that you use in order to communicate this is consuming. So that is a huge problem. And then you will have more or less the same from here to here. So that's first disadvantage. The other is what happens if I overcharge my processes here. If I have heavy processes within my mappers, this can also create overhead. So it's an optimization problem to have a balance in the complexity of the execution of the functions that are implemented by the mappers, and with respect to the number of processes that will be running and the number of messages that will be passing to communicate this within the infrastructure, right? So that's the problem that we have to address. So if we already have the pattern, we do not longer have to address this design problem. We can refer to the pattern. We know that experimentally this has been discussed, and so we can be confident that in a classic setting of the solution, we will run in a performant manner. Questions until here? Timing. Yes, please.
Yes, teacher, what is a pattern? Could you refresh my mind? It's just,
Partitioner?
no, pattern.
Pattern.
Yes,
Did you study in software engineering the gamma patterns?
the gamma part.
Gamma, los patrones de gamma.
Pattern. No, I don't remember.
No?
No, no.
Okay, so it's like no because you don't remember. Okay, so in software engineering, the software engineering community um, observed that when we when we have to develop algorithms, we have to make decisions on the data structures we use and the strategies that we use in order to implement those algorithms, and that these strategies are recurrent. For example, if I have to implement a linked list, of course, the elements of my list can vary, but the strategy or the set of strategies that I can adopt are finite, are more or less the same, and are recurrent. Okay, so what the software engineering community said is, if this is recurrent, we are going to represent in patterns like a recipe of what do you have to do if you have to implement, for example, a linked list or a B tree. And more than that, and which are the problems that I can address with, for example, this data structure. Such that when nobody can master all the algorithms in the world, that's not possible. Okay, so when I have to a problem, I look for the problem in it's a kind of dictionary. I look for the problem in the dictionary of patterns, and I go to the pattern, and it describes the recipe that I have to adopt in order to implement this. And there is a famous book. The author is Gamma, and you have it's a book like a very heavy book where you have the programming patterns. Okay? And so, inspired on this Gamma Patterns book, the MapReduce community came up with MapReduce patterns. So I think that even in, I mean, well, first of all, is this notion of pattern more or less clear? No.
Yes, it's just that yes, it's the same pattern. It's just that the game gamma didn't appear.
Well, Gamma existed a long time ago, so he didn't address. I mean, this MapReduce story, it's like 10 or 15 years old, so he couldn't have a look at that. So you have the Gamma patterns, addressing many patterns, programming patterns, and then the MapReduce community proposed a version of patterns for MapReduce. But the notion of pattern, you get what it is, okay? Like this recipe. Well, I mean, the recipe looks like my slides, okay? So you have the description of the problem, the intent, the way you can generally define the problem and the solution, and then the architecture that you have to consider in terms of processes on how your solution will be deployed in a target machine. And then it goes further, because here I'm not touching any programming language. In fact, both Gamma and this book tells you how to implement this in Scala, in Java, in C, etc. So you really have a huge help when you have to program a solution. Everyone clear?
Yes, thank you, teacher.
You're welcome. The others? Right? Okay. So I am going to profit to tell you that like physicians have their books, no? They have the anatomy of I don't know who. Or, any physician has this book in his or her library. You know? And other books like that. So if we do the parallel in computing systems engineering, and we think about the kind of books that we have to be acquainted with, well, one we have already referred to, it's Aho and Ullman for principles of compiling, etc. So there's principles of programming, and then there is compilers, okay, and interpreters. These are both books important. Of course, if you get the job of your life, or if you finish your studies with summa cum laude, and a nice gift that you can ask for is the Encyclopedia of Knut. No? That's the set of books of our discipline. If you should also have in your library at least 3 or 4 books, fundamental books of databases, which is Corf, which is the one of El Masri, no? The Ullman and Jennifer Williams book, Gerke's book, the one of the cows. That's the books that someone should at least be acquainted of for DBMS, relational DBMS. If you are very fancy, you can add Tamer Otsu and Patrick Valdurier's book, who has been, the last edition came up, I think, last year, with new views of data management systems. So that's another book that it's important. Then if you have, you learn distributed systems, Tannenbaum is a very important book. And you have 2 Tannenbaums, the one for operating systems and the one for distributed systems. So these are important books. And then for computing engineering, well, you have this Stanford's book, a very big one about algorithms. Of course, that one you have to have, and then gamma patterns. You should have this in your electronic or in your physical library, but to make sure that you are acquainted with these books and that you know them. This is part of your education and your culture about your profession. So it's very important. Yes, and most of them are now you are like people of the 21st century. So it doesn't matter if you have them physical or online, but you have them because this is important. Okay, so that was for this first acquainting story of. I have to look to my watch to make sure that we have time. Yes, please, Francisco.
And I just included a link to a public library from which you can download almost any book you want for free.
Yes, LibGen is the library. But it's not, we all know about it, but we shouldn't say this. No, but in fact, for example, Ullman's books, you can find them. I mean, maybe not the last edition, but some of the editions are in his page. And there are slides and exercises available for anyone. So people work in general, people working in Stanford or in American universities, important American universities, have the material available. So there's no need to go and have a look to alternative libraries. Knut, for example, that's something that it doesn't exist like that, I think. The others you can have access to. And Gamma, I would say I will have a look. I have the impression that, well, as long as the war does not continue, because at some point we will be cut from Russian provision uh, of knowledge. Okay. Well, we got acquainted with. Yes, Ryan, please. Sorry, I didn't see you.
Sure. One question regarding the road. Uh, I want you to give us at least one more day to finish or have the chance to upload the. So if it's possible.
Yes, in fact, what I was realizing is that Monday is free, no? It's holidays. So what I will
Yeah.
do is I will extend to Tuesday so that if you need a little bit more time on Monday, you can have a try on it, and so I will change to Tuesday. Okay.
Thank you very much.
Yeah, you're welcome. No worries. Yeah, yeah. No, martes, Tuesday, not Thursday, Tuesday. Right. Anyway, what I will do is I will change the Blackboard deadline, so and you will certainly receive the notification, so that everyone is clear. And of course, you will have right to upload the the report. Okay. So yeah, that's thank you for reminding me, because I thought that I would do that, but then I started with these stories and then I forgot. Of course, because it's not me that is having to hand in the report. But yes, I have considered this. Okay, other questions? If you don't have questions, I have questions for you. At some point, someone in the previous session asked, what are we learning this for? Okay, these parallel map-reduce stories, and what is the line of reasoning that led us from the cloud at the very beginning of the lecture and now here on these more algorithmic issues? Can someone tell me, why are we learning this? Yes, please.
Okay, it's about map reduce, right?
Yes.
Yeah, the algorithms. Okay. So
Mm-hmm.
basically, we're learning this in order to know how to. Well, first, what I will hope I'm right. Parallelization is because it's very important to know how to parallelize between a distributed environment, because we have nowadays have a lot of information that we want to aggregate and group. So MapReduce is a good way in order to partition this big data into different nodes and parallelize the process in order to do more efficient processing, and that adapts to these new types of technology. How about that?
Okay. Before I comment, do I have other tries? Do you agree with Mauricio? Nobody agrees with you, Mauricio. They don't agree. Is his answer complete? I mean, you will not see him, so he will not be angry with you if you say that his answer is not complete. Will you? You won't be angry. No? You will not challenge anyone in a battle because they do not agree with you. Nobody? Okay, so I'm going to comment. Yes. He's open about any career. Profit from this this opportunity. Okay, if you cannot comment, you're right. I mean, the problem is that we have to deal with a lot of data, and in a centralized setting with a classic architecture, either it is not possible or it would be very, we would have to wait for a long time, or yes, the architecture wouldn't be prepared for this. I think that that you are missing in the reasoning is the fact, the algorithms. You see, the algorithms that it's of course about the amount of data, but it's also about the type of algorithms that we use in order to process the data. Okay. So, of course, if we are talking, for example, with this first family of classic aggregative operations, this is not very evident because, I mean, um, the difference between parallelizing or not would be seen with really huge amounts of data. Otherwise, it will not be very explicit. But there are other algorithms, particularly, for example, when we start moving into filters, when we start moving into joins, And now can you hear me?
Yes. Yes.
Yes.
Yeah. At some point, I didn't even realize that I didn't have the camera. I don't know what my machine decided to do today. Right. Okay. So what I was saying is that, in fact, so in order to even be able to execute the families of algorithms that are really greedy, we need alternative architectures. Okay. And when we have these alternative architectures, we should be able to exploit. I mean, if we have several CPUs, we need to be able to exploit these new sets of resources. Okay, and in order to be able to do that, we need alternative programming models, and MapReduce is one of them. So for one side, you have what Mauricio said. Of course, we have a lot of data. We need to process these huge amounts of data, and so we need resources in order to be able to exploit them. Why? Because the operations that we often apply to this processing are greedy. So that's one piece of the puzzle. And the other piece of the puzzle is that once we have to learn how to exploit not only PC or desktop, but to really explore, be able to use other computing architectures. Okay, and one computing architecture that is famous of providing new resources is either clusters or data centers, like in high performance computing centers, or the cloud. Okay, so there we have new architectures in many senses, several processors and several types of processors, several disks and several types of disks, and all this together makes the architecture different. There are different constraints in order to use it and exploit it, and we are learning how to exploit these other architectures, okay? So that you do not end up just being able to use personal computers or servers. But I mean, uh, one self-included system. And then from the practical manner, it's many application requirements that are around these days require to be implemented and executed in these new types of architectures, either because they use a lot of data or either because they are greedy in their operations and they need to have these alternative architectures. And so this is the third column: applications with resources requirements, new architectures that we have to learn how to use and exploit, and big data collections characterized by volume and velocity that need, again, this type of architectures in order to be processed. Okay, and this is the reason why we are here in this arid setting of MapReduce. Then, as I said, we will move faster, but you have to get acquainted with this. Right? Clear? Not do as you said in statistics that I asked, that someone asks, why are you learning statistics, and you do not know. Make sure that every piece of knowledge that we discuss here, you know what it is used for and why you are learning this, okay? So before we close the session, we're going to watch a video. Let me try to see whether this thing doesn't make me do suffer. Well, I'm going to play and
Dia Messi, capital of Catalonia.
Can you hear?
Yes, doctor.
Yes.
Okay. So,
Welcome to Barcelona, home of Gaudí and Messi, capital of Catalonia, where the Mediterranean weather, gastronomy, and culture welcomes visitors from around the world. This background noise that you can hear now is Mediterranean, but it's not the sea. It is Mare Nostrum, the main infrastructure of the Barcelona Supercomputing Center, where we do both research and provide services on supercomputing. Let's go inside. Nowadays, pretty all the scientific disciplines need and use supercomputing technologies to accelerate the generation of new knowledge. Any problem that can be translated into computer code can be treated with a supercomputer. This research infrastructure is mostly devoted to science. To get access to the systems, applicants can request peer-reviewed supervision, and only the most excellent and brilliant scientists get access to those. If I have to choose among the projects supported by us last year, I have to mention the move forward on personalized medicine, and also the detection for the first time of the gravitational waves predicted by Albert Einstein, work performed by Sasha Husha from Balearic Islands. In my research, I'm interested in the gravitational wave signals, which are created when two black holes collide, the most violent events in the universe. And my particular job is to solve Einstein's equations and calculate with very large calculations what such collisions look like, what exactly are the signals that are given off. Experimentalists in the LIGO collaboration can compare my predictions with the data and find out which systems have created these signals. And for these calculations, we have to use very large machines. My home machine is Mare Nostrum here, which today I have seen for the first time. I log into this machine almost every day. And the importance of it for our work is very easy to explain. Without this machine here in Spain, we could not do the kind of work we do. We would have to change our direction of research and do something else. We cannot do large calculations. We work in a university hospital here in Barcelona. Our main interest is the study of a particular type of cancer that originates in blood cells, leukemias and lymphomas. And thanks to the new technologies to sequence the DNA, we are now able to analyze the genomic alterations of these cancers. We compare the sequence of the DNA with other layers of information. To integrate all these different layers of information, the supercomputer here is helping us to obtain a very clear information. More important, we are discovering new targets for new therapies that for sure will improve the quality of life of our patients. My research is focused on the computational fluid dynamics and specifically about the simulation of the wind speed around the wind farms. Thanks to this supercomputing, we are able to go one step above in the simulation of the wind speed, going to the next level of the computational fluid dynamic models.
So, I'm going to stop sharing my screen. So now you want to go to have an internship at the BSc. It is possible. Okay, so if you're interested in such kind of opportunity, contact me and we can see whether it is possible to put you in contact with people that can use this. But anyway, the idea of the video was to show you that these data-driven problems require, of course, infrastructures like the one we have seen, but they also require people like us providing programming solutions, implementation of models and methods so that they can run smoothly on top of this architecture and that people can profit from these results and solve problems of the humanity. Okay, so this is all about being able to run nice algorithms on parallel computing. Okay, so with this, well, if you have questions, this is the moment to ask before we close the session. Yes.
So teacher, so we want also like MapReduce in order to like we already have like algorithms, but now we want to them to have them in parallel in a parallel
Yes.
way, right?
Yes.
Okay.
Yes. And there, well, there are applied mathematicians, for example, are all their one of their jobs is to figure out which is the best parallelization setting for existing algorithms so that they can run smoothly in different machines. So a contribution would be, I have an algorithm, I don't know, for deep learning, and then I come up with a parallelized version that can run on top of GPUs in order to address, I don't know, cancer identification of cells, cancer sequencing, for example.
Oh, that's cool.
Yeah, that's very cool.
Okay. Thank you, teacher.
You're welcome. So, if there are no further questions, we're going to stop here. As I said, during the day, you will receive the notification of the extension until Tuesday to hand in the second round of the regular course graded exercise. And we will see each other on Tuesday for the lab. Have a nice weekend. Yeah, nice weekend.
Thank you, doctor. Have a nice weekend.
Same to you. Have a nice weekend. Bye bye.